Good morning. This is Dr. Kumar Arya, Associate Professor in Department of Chemical Engineering, IIT Jalandhar. Today I am going to explain heat transfer in two-dimensional metal block. So heat transfer in two-dimensional metal block is given by this Laplace equations. So if we see the Laplace equations is given by this particular format. So let's see del square t upon del x square plus del square t upon del y square. So is a metal block we are considering at 1 meter and 1 meter in size, such that its four edges are kept at different temperatures. So if we see the figure of metal block is something like this. So here in this case, so this is the metal block here, this one, and its four boundaries are kept at different temperatures. Here temperature is 60 degree, here 35 degree, and here in this case we have the 100 degree, and here we have 70 degrees. So we have all four sides are being kept at different boundary temperatures, and our purpose is just to calculate the temperature at different nodes here. This node 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the 9 temperatures are supposed to be calculated. This end is complete boundary, so it will gain the temperature this corresponding to this boundary conditions. This is the bottom side here, which will gain temperature here, this one 35. These one 4 would consider the temperature at 100 degrees Celsius. All these one will consider the temperature at 70 degrees Celsius. So let's see how to calculate it. So the Laplace equation is given by this one, del square t upon del x square, del square t upon del y square. Now this can be solved for any mass size, so we have taken the finite difference formulation for that, for square mass. So square mass means we have considered equal number of points in x direction, equal number of points in y directions, so that we will get a square mass actually. So finite difference formulations using central difference formula for second derivative of temperature is given by this. So this T I minus 1 minus 2 Ti plus Ti plus 1 upon h square, where h is the step size. Same thing for this y square, del square t upon del y square would be equal to this Ti j minus 1 plus 2I j. So here j is getting changed, j minus 1, j plus 1, and the step size here in y is considered as k. Now this Tij is temperature as position at ij. Ij are the numbers of difference point between boundaries x and y, where I will change from 1 to n, j will also change from 1 to n. So for let's say for mass size 3 and 3, so for 3 and 3 mass size, this will look like our system. So this here, for this particular corresponding point, let's say we have moved to I equal to 1. Now j is getting changed from 1 to 3, then I equal to 2, j is getting changed from 1 to 3, I equal to 3, j is getting changed from 1 to 3. So by considering this, so for 3 by 3 we will get this type of matrix. Totally we have here 9 elements, 9 by 9. square matrix. So the first row will give these elements, one here, this 1 upon k square, then 0, then upon 1 upon h square. And here we say that each term, first row would have only 3 terms, second row would have 4 terms, 1, 2, 3 and 4. Then now you see from each side it is getting shifted one to the right side. Now this is 1, 2 and 3. Now it has reached to the fourth number. The fourth one will have 4 terms, 1 here, then this main diagonal terms, then the off diagonal terms, that is 1 upon h square. Then this pattern will continue. So this is continue here, this is coming something like this here, completely a diagonal matrix. This is also changing here, the k square, this 1 upon k square, 1 upon k square, then 0, then upon k square, again 0, again k square, again k square. Same pattern is this side, 1 upon k square, 1 upon k square, 0, 1 upon k square, 1 upon k square, 0, 1 upon k square, 1 upon k square. So this looks a interesting matrix, so it need to be generated by thinking it carefully how to generate it. Then these are the unknown temperatures, so these are coefficients of T11, T12, T13, T13 only. Then you have T21, T23, then T22, then we have T31, T32, T33. So these are the all unknown temperatures. These are coming from boundaries here, so wherever you are getting 0 either of the side, that's the boundary. So T01, T12 upon k square, then here you have T02 upon h square. So all these are the known values of the temperature here, which can be calculated and substituted back. Now let's see how to generate this matrix. So this matrix can be generated by substituting I equal to 1, j equal to 1. So you'll get this row. So where we are getting these zeros, these are already known to us. Now we have substituted an I equal to 1, j equal to 2, we are getting another equations. Then I equal to 1, j equal to 3, another equations, then I equal to 2. Now we are changing j from 1, then 2, then 3. So these equations are coming. Now I equal to 3, again we are changing j from 1, then 2, then 3. So again these one. Now similarly it can be generated for any mesh size is 2 by 2 also. It can be given in matrix format. So T 2 by 2 the matrix will look like that. So it's same as previously, but it's with the smaller form of that one. So it won't give you the clear idea as compared to the previous one. Now 3 by 3, this is a good one here. So this will give you correct idea how the elements are being generated and what patterns are they following. So this is matrix, and somehow we have to think how can we generate it. Now we have given a scheme how can we generate this matrix. So for any I, this is main diagonal term. Here is given 2 upon h square minus 2 upon k square will generate the principal diagonal terms. The element of fourth diagonal of right and left side would be generated by this, here by this particular commands. We have come out with this one. So this command will generate fourth diagonal left and right both. Now left and right diagonal adjacent to principal diagonal will be generated by this, by putting a condition here I is greater than equal to 2. So is being generated by this particular format, by this one. Now we are putting if I plus 1 or I minus 1 equal to n plus 1, comma 2n plus 1, 3n plus and so on, then we are substituting the elements here 0, so that it will take care here the 0 term. So by putting that, the matrix is being generated, and then a MATLAB code is being written for that, and this is how we have got the temperature calculations at different nodes. So this is the MATLAB program for that. So 1 by 1 slab, so 1 meter in x, 1 meter in y. Here and here number of grid points we have taken, n is 3 in both the sides, so saying square matrix. Now here we have generated this principal diagonal matrix here, then left and right side of principal diagonal by this one here. Then we have generated second diagonals of left and right side by this commands, and then we are putting the condition here just to calculate this last row. Then we are putting another conditions here so that we have calculated 0 elements, and then we finally have calculated the boundary condition matrix here, boundary conditions. So boundary conditions are 4 boundary conditions are there. Boundary condition 1, 35 degrees Celsius. This is at 0, x will change, y will not change. The second condition is boundary condition 60 degree. Here for x will not change, x equal to 0, y will change from 1 to 3. The third boundary conditions, that end of the slab in x directions, so x is fixed, y will again change, the y again, then now x will change, y will not change. So top boundary conditions here. So by substituting here, we are conditioning the boundary condition matrix here. The inverse of that, this is being calculated and generated, and then again we are plotting here the boundary conditions, and finally we have solved this. And once we have solved this one, we will end up with this result. Actually, this were the results once we will generate it and solve it. And for more information, detailed informations for heat transfer solutions, readers can read our papers here where we publish all the results. Thank you.